Hi, my name is Kevin Napier. I'm a third year graduate student at the University of Michigan studying physics and the Kuiper Belt. So first of all, I want to thank you for the opportunity to speak today. I'll be talking about the apparent clustering of a class of solar system objects known as the extreme trans-Neptunian objects and what that might mean for the hypothesized planet X or planet 9. So I'll start with a brief history in case people aren't familiar. In 2014, astronomers Chad Trujillo and Scott Shepard noted an improbable clustering in the arguments of pericenter of the most distant solar system objects known at the time. And just kind of in an offhand comment in this paper, they said that maybe a massive planet could cause this to happen. In 2016, Konstantin Batygin and Mike Brown from Caltech took a closer look and sort of defined a class of objects known as extreme trans-Neptunian objects, or ETNOs, and found that a massive eccentric planet of 5 to 10 Earth masses at a semi-major axis of about 500 AU could cause clustering in the longitude of perihelion and the longitude of ascending node of these objects. In 2017, the Outer Solar System Origin Survey, or OSOS, a group which discovered a handful of the known objects, analyzed their ETNO discoveries and accounted for the bias of their survey. And when they did this, they noted that the apparent clustering might not be a real effect, but rather just an artifact of selection bias. In 2019, Brown and Batygin took another look at this problem, this time trying to account for selection bias in the entire population of known objects. So they devised a method in which they sampled from minor planet center, and this algorithm tried to heuristically build up a bias map. And they determined that the clustering effect is real at something like 3 sigma. And then finally, most recently, in 2020, our collaborators on the Dark Energy Survey tested for the isotropy of these angles in the Dark Energy Survey's 5 to 8 detections, however you slice the ETNO population, and found that they couldn't reject the null hypothesis that these are drawn from a uniform underlying distribution. So now with that history out of the way, I'll get to the physics. So this is the current state of the Kuiper Belt as of about a month ago, and I'll now overlay the known extreme TNOs or ETNOs. And so there are fewer than 2 dozen of these, more than 20, fewer than 2 dozen, depending on who you ask. And I've defined these as semi-major axis greater than 230 and pericenter distance greater than 30 AU. There's not really a consensus on the classification of these objects because there's a lot of debate about whether they're being defined as a function of the Planet 9 hypothesis. But we'll go forward with this as our working model. So if you plot the orbits of these, you get some more dynamical information about them. And so here's the apparent clustering. The supposed clustering is along this axis that I'm showing now with my cursor. And there's also a second axis of clustering that is in the planes of the orbits, basically. They're orbital poles. So the claim is that they tend to share a common plane. But all of this, so if you just look at these, they look clustered, but all of this misses the question, what about survey bias? These objects are on very long elliptical orbits. They're not enormous, so they're pretty hard to detect. And they're only observable within about a decade of perihelion. So that means that the longitudes become strongly biased as well for their observations. So where you pointed the telescope and how deep you were able to observe will have a large impact on what you can actually see. So it turns out that 3 well-characterized surveys have discovered ETNOs, and luckily they've discovered 16 of the 20 or so 80% of the population. Here, for this work, we'll break these 3 into 4, because for reasons that I won't get into, the dark energy supernova fields need to be modeled differently from the rest of the survey. So with these 3 surveys, I've now colored the ETNO orbits, and the light gray ones are objects that were discovered by surveys that don't have enough information to compute their biases. So getting rid of those, this is our final sample. 16 ETNOs discovered about evenly between 3 different well-characterized surveys. So with that out of the way, the next step is to actually simulate these surveys in order to compute their biases. So to do a really thorough survey simulation, one would create a synthetic population of objects, propagate them to all of the survey's observation times, compute topocentric ephemerides and color-corrected magnitudes, reject sources near bright stars, compute which CCD the objects fell in, account for chip gaps, dead pixels, etc. And then you would fold in the detection efficiency into those synthetic detections, and then you have your set of synthetic detections on which you can do statistics. Many of these steps are computationally intensive and require more information than is available. So we decided to make a really simplified simulator in which we eliminated all of these steps to get down to this simplified algorithm. So we generate a single population. So we're just assuming that the surveys took all of their data all at once on one date. And then we compute geocentric ephemerides and visual magnitudes, because at this level of analysis with only 16 objects, those minute differences are not going to matter. So then we compute the survey ephemerides and limiting magnitudes and fold in the follow-up strategy, and that gives us our synthetic detections. So there's a lot of assumptions made there, so we did some quality checks. And for the same set of priors, we used our survey simulator and checked it against the proven ASOS survey simulator. And ours is in red here, and the ASOS is in black, and these distributions are statistically indistinguishable using Kuiper's test, which is a cyclically invariant KS test. So we're confident with the fidelity of our simulations going forward. And then the final piece of business is to construct an orthogonal basis. So one complication is that the longitude of pericenter is just the longitude of ascending node plus the argument of pericenter. So these variables are very strongly correlated. So you need to break them into an orthogonal basis in order to do any statistics on them. Luckily for us, Batygin and Brown did this in their 2019 paper, and these are just the Cartesian analogs of the Poincare variables, actually properly scaled by eccentricity and inclination. So this is the phase space that we'll work in, and so in these figures below, the blue points are the actual ETNO detections, and the red point is their mean. So again, checking against the ASOS survey simulator, this is for the same set of simulations as I showed a couple of slides ago. We match with high fidelity, so we're confident going forward. So then our final question is, can we reject the null hypothesis? In this case, the null hypothesis is that the ETNOs that have been observed are drawn from a uniform underlying distribution. So we set up a population model with some semi-major axis eccentricity and inclination distributions chosen from the literature, and then we generate objects uniformly in their longitudes and with some range of mean anomalies for which they can be discovered. And then we run simulations until each survey has discovered millions of objects. And those millions of objects are plotted here in density maps, and the posteriors are the black points, the black contours, and the actual detections for each survey are the blue points. So then you sample from this millions of times in order to compute a p-value that these points were drawn from these distributions. But in their 2019 paper, Mike and Konstantin did a different approach in which they sampled from these distributions n points, where n is the number of ETNOs detected by each survey. So for DES, it would be 5. They took their mean value and then plotted it onto this axis and built up those mean sampled distributions. And then you plot the actual detections in red, and then you can integrate in this 4-dimensional space to get the p-value. So we did both ways so that everybody would be happy. And this is the result for the supernova field. It only discovered one object. But so a p-value of less than 5% would be significant for those distributions I showed before. And for each of the 4 surveys that we considered, none ever had a p-value that small. So we these values are for doing the statistics in the two different ways I talked about, and for slicing the ETNOs up into different subcategories based on some people think that different ETNOs should be treated differently because they seem to be dynamically special, or some are more detached from Neptune than others are. But no matter how you slice it, you never get a significant deviation from the null hypothesis with a single survey. So then finally, we needed to compute the joint probability, and the joint probability is just the set of outcomes as likely or less likely than what you detected. So formally, that would be the volume underneath the surface of constant product inside the domain of the n-dimensional unihypercube, where n is the number of surveys. So in 3 dimensions, that's just this picture where this yellow is the surface of constant product, and that volume is expressed by this series. But the bottom line is that we never had a significant rejection of the null hypothesis in any way that we slice up the data. So one last figure that I'll show is this. So on the radial axis is barycentric distance at discovery, and the azimuthal axis is true anomaly at discovery. And the white is the survey sensitivity. So I've here combined the survey of Shepard and Trujillo, ASOS, and DES. And the red is the things that they actually detected. So this is a pretty powerful visual representation that says we find things where we look. And we haven't found things elsewhere because we haven't looked there. The reason that we don't find anything along this axis, it could be because Planet 9 is shepherding things here, and we just happen to look exactly where Planet 9 was shepherding things. But this happens to be the galactic plane, and you can't find TNOs as well in the galactic plane, so people don't typically try. So that is a visual demonstration of these biases. So in conclusion, while we cannot explicitly rule out Planet 9, we can say that it is not required to explain the ETNO data, and thus the ETNOs are not necessarily clustered to begin with. And I'll take any questions now.
Thank you. Very, very interesting. The floor is open. We have a few minutes.
Can I ask a question in audio?
Please go ahead. If you keep it short.
Do you have any reason to expect that the upcoming new survey instruments, particularly the one in Chile, will change this? Have you looked at that?
Do you mean LSST?
Yes.
Yeah, so LSST will discover hundreds of these. I haven't looked at what its sensitivity will be in terms of this plot, right? But it will have coverage where we have not found any ETNOs yet. So hopefully it will discover on the order of 100 new things, and it will have well-characterized biases, and then somebody should do this again. But until then, I don't think it's worth it.
Thank you.
Or it might find Planet 9. You know, that could happen too.
Or that too.
Okay.